We're now going to evaluate a double integral over a rectangular region, but we're going to use a geometric argument based on the fact that this double integral represents the volume between a surface and a region in the xy plane. So as a reminder, this double integral is going to have an integrand that is a surface function. So if our integrand is 5 minus x, essentially that means that we're looking at the surface function where f at xy, or z, is equal to 5 minus x. So let's begin by graphing this surface and see the rectangular region in the floor over which we are to find the volume. So this surface function, f at xy is equal to 5 minus x, is the plane z is equal to 5 minus x. So that because of the fact that we are missing the y variable, we can think of this as a line in the xz plane with a z-intercept of 5 and a slope of -1. So we can then take this into R3. We'll graph this same line in the xz plane. And in R3, this point is 0 in the direction of x, 0 in the direction of y, 5 in the direction z. And down here we have x is equal to 5, y and z are 0. So here's that line. Before we do too much with this drawing, let's remember that the region in the xy plane over which we are to find this volume is from 0 to 5 in the direction of x and from 0 to 3 in the direction of y. Now, because we are missing the y variable, this plane would be obtained by flying these ordered triples in the direction of the missing variable y. But we really only want to go out to y is equal to 3. So before we do too much with this graph, let's actually look at that region in the floor to ensure that we are not going farther than is needed. So when y goes from 0 to 3, that means that we're really only flying this out 3 units in the direction of y. And if we look at this box, we can see that x is going from 0 to 5, y is going from 0 to 3, and this is our rectangular region in the floor. So while, yes, we are extending these ordered triples in the direction of y, we don't want to go too far. We don't want to go beyond the y is equal to 3 value. So this is really the only portion of the plane that we're interested in, and we want to determine the volume of this region here that is between the surface and that rectangular region in the floor. And let's call this our rectangular region. So let's recall the volume of any cylinder is going to be determined by the area of the base multiplied through by the third dimension, or let's call it the height. So this triangular cylinder is kind of on its side here. We're going to consider this rightmost wall to be the base. So we're looking for the area of this triangular base, and then we're going to multiply it through by this height dimension, which is actually going to be determined by the length of this side here. So the area of this triangular base is going to be 1/2 of the base times the height for a triangle. Let's use this side here as our base side, which is going to be 5 units long in the direction of x, and this vertical side over here, the height side, which is also 5. So the area of this base is 1/2 times 5 times 5, which is 25 divided by 2. So down here, let's say that the area of the base was 25/2, and now we're going to multiply through by the height, and this height measurement is going to be 3 units long. We went 3 units in the direction of y. So the height value is 3 down here. We multiply all this together to get 75/2. Now, if we had the units, we would put that here, but for right now, we'll just say this is going to be units cubed because of the fact that we have a volume.